So in this video, we wish to give the statement of the closed graph theorem. And actually, there's a very simple proof for the closed graph theorem that's based on the open mapping theorem, or the consequence of the open mapping theorem. And we would like to give this too. So first of all, let's begin with the statement and let's try to understand what the meaning of this theorem is. So here's what it says. Let x comma y be Banach spaces, and t from x to y be a linear map such that its graph and we can define the graph as a set of pairs of x comma t of x for x in x, which is a subset of x times y, is a closed subspace of 10. T is a bounded linear map. Okay, let's try to understand the significance of this theorem, because it's a theorem that really simplifies a lot in many cases the task of trying to show that a linear map is continuous. And we need to try to appreciate this. So in general, if you want to show that a linear map is continuous, then you can try to do two things. You can try to show that, so if, let's say, x comma y are Banach spaces, let's use a different color here, since we're done with the statement of the theorem and we're not proving it either. We're going to prove it actually, but let's discuss it first. So let x and y be Banach spaces. And t from x to y a linear map. So somebody might ask, is this map continuous? Okay, we're not going to answer the question. This is a theoretical question, and we just want to see how it can be answered. So normally, you could try to do different things. So first of all, you could go with the definition of continuity and try to show that if t, if xn converges to x in x, then does this imply that t of xn converges to t of x in y? If the answer is yes, then t is continuous. If the answer is no, then, or you can find a counterexample to this, then t is not continuous. The other thing that you can try to do is the set of all t of x's for x with norm less than or equal to 1 bounded. So you can ask this question. Okay, what I would like to show you here is that the closed graph theorem really simplifies the first method vastly. Because what does it mean for a set to be closed? It means that it does not let its sequences converge outside the set. So basically, what closed graph means is the following. So first of all, one of the things that one should note here is we're looking at this Banach space, the product of the two Banach spaces, which consists of all the pairs. And we can ask, how is that a Banach space? What is its norm, first of all? So on x times y, we can consider the norm. So if we have a pair, x comma y, in this space, then its norm can be taken to be the sum of the norm of x in the space x. So that's why I'm putting this subscript x to show that this norm is taken in x plus the norm in y. And the truth is that this is one of an infinite number of equivalent norms that we can consider. This norm is rather convenient. And this norm works coordinate-wise. So if you have a sequence xn comma yn in xy, then that converges to x comma y if and only if xn converges to x and yn converges to y. And pretty much that's what I meant when I said we have an infinite amount of norms. There are an infinite amount of norms that allow this condition, and this is precisely the condition that we want for the product. So now, if we go back to the statement of the closed graph theorem, let's try to understand what it means for the graph to be closed. So let's denote by G the graph x comma t of x. That's what the graph is. We juxtapose input and output. And as I said, this is a subset of x times y. So remember that a set is called closed if it does not allow its sequences to converge outside, meaning if xn comma t of xn, that's what a sequence in G would look like, converges to an element xy, then xy should be in G. Yeah, but what does it mean for xy to be in G? It means precisely that the second coordinate is the image of the first coordinate. So y has to be t of x. So in other words, what one needs to check in order to establish the conditions of the closed graph theorem is that if xn tends to x and t of xn tends to y, then t of x is equal to y. If this condition holds, then the conditions of the closed graph theorem are true, which means that you have an extra tool. You're supposing that t of xn converges to y. In the original statement of continuity, you just want to take t of xn and show that it converges to t of x. And that might be a much harder task than assuming that the sequence t of xn already converges to a point in y, and only having to confirm that that point has to be the image of x. So in other words, it gives us a much more powerful scenario than the general scenario that we need to check for continuity. And that's why it might be a good idea to even restate the closed graph theorem without stating anything about graphs. So I could do the following. So I could tell you that this statement that I'm going to give you is equivalent to the closed graph theorem, only there's no graph mentioned here. So let x comma y be Banach spaces. and T of x, y, T from x to y, a linear map, such that if xn converges to x in x and T of xn converges to y in y, then T of x is equal to y. Then T is a bounded linear map, meaning a continuous linear map. Okay, so that's precisely the way that the closed graph theorem is used, and we can give this statement that doesn't allude to any graph. I mean, certainly it's not a bad idea to know both statements, but this is pretty much how it's used. And I promised you that I would actually prove the closed graph theorem for you. And here's how it goes. So consider the two projections. Projection onto x from x cross y to x, which sends the pair xy to x. Then this is continuous. Why? I mean, this is where this norm comes very handy, because if you take the norm of the projection, which is really the norm of x, then this is less than or equal to the norm of x comma y, which is the norm of x plus norm of y. But this inequality really tells us that we have continuity. That's what continuity is, that for linear maps, that the norm of the image is less than or equal to a number times the norm of the input. So this is continuous. Okay. But here there's another interesting thing, that if we now take, if G is the graph of T, and it's closed, then G is a Banach space. And if we restrict the projection onto X on G, then it is one-to-one and onto. This pretty much, this is nothing exotic. This is the nice old principle that we must have seen in Calc 1, where a function is really the same thing as its graph in some sense. Meaning, if somebody gives you a geometric curve that has the general that satisfies the vertical line test, then having that curve is the same thing as having a function, because you can simply take an x and associate it with its corresponding point, and then take the y. And in this case, if the function is continuous, then going back and forth between the curve and the interval is an operation that at least identifies this as metric spaces. So here, of course, it's the open mapping theorem that tells us that since we have two Banach spaces G and X, so the projection goes from G to X here, and it's one-to-one and onto, then especially because it's an onto map, it has to be open. And any linear operator, linear map, which is one-to-one onto, and it's open, open means really that the inverse map is continuous. So that tells us that this is an isomorphism between the two Banach spaces. So isomorphism means exactly that the two Banach spaces are really very, very similar objects. Or for practical purposes, it means that the inverse map from X to G is continuous. That's all that matters here. Because now, basically, I can think of going from X to Y through T in two steps. First, I go from X to G, okay, which is a continuous map. And secondly, I go from G to Y. And here I take the map that sends X to X comma T of X. And here I take the projection onto Y. So this map from X to G is an isomorphism. Why? Because the map from G to X, I'm sorry, from X to G is continuous. Why? Because it is really the inverse map of the map from G to X of the projection, which has an inverse continuous thanks to the open mapping theorem. And then it's composed with the projection onto Y, which is a continuous map. So again, the continuity of this map is established, continuity of this map. Established by the open mapping theorem. Okay, the open mapping theorem says that any one-to-one and onto continuous linear map between two Banach spaces has a continuous inverse. And this is the inverse map of the projection. Remember, the projection sends X comma T of X to X. The map that sends X to X comma T of X is the inverse of the projection. So now basically what we have is T is the composite of two linear maps, and hence it's continuous. And that's pretty much the proof of the closed graph theorem. So the closed graph theorem is based on the open mapping theorem. The open mapping theorem is much harder to prove here, but there are actually contexts in which one proves the closed graph theorem, and then the open mapping theorem follows in a simple way. The bottom line is that we chose to take the other route, and here we just established that the closed graph theorem is an easy consequence of the open mapping theorem. And that's all. Thanks for watching.